Have you ever wondered how one of the strongest and most versatile metals on Earth is made? Titanium is a material that quietly powers some of the most advanced technologies in the modern world. It is used in jet engines, spacecraft, medical implants, military equipment, and even luxury watches. Despite its incredible strength and resistance to corrosion, titanium is surprisingly lightweight. These unique properties make it one of the most valuable metals in modern engineering. But titanium does not come out of the ground as a shiny, finished metal. Its journey from raw mineral buried in the earth to a high-performance material used in aerospace and medicine is long, complex, and fascinating. The story of titanium production is a perfect example of how science, engineering, and human ingenuity work together to transform natural resources into advanced technology. Titanium is actually one of the most abundant elements in the Earth's crust. In fact, it ranks as the 9th most abundant element found naturally on the planet. However, even though it is common in nature, pure titanium metal is extremely rare. The reason for this lies in the element's strong chemical behavior. Titanium has a powerful attraction to oxygen and other elements, which means it rarely exists in its pure metallic form. Instead, it is almost always found locked inside minerals and chemical compounds. The two most important minerals that contain titanium are ilmenite and rutile. These minerals contain titanium combined with oxygen and other elements, and they are the primary sources used for industrial titanium production. The journey of titanium begins with mining. Titanium-bearing minerals are typically extracted from large open-pit mines located around the world. Some of the biggest producers of titanium ore include countries such as Australia, South Africa, Canada, China, and India. These regions contain large deposits of ilmenite and rutile sands that were formed millions of years ago through geological processes. Mining companies use massive excavators, trucks, and industrial equipment to remove the layers of soil and rock that cover the titanium-rich mineral deposits. Once the ore is extracted from the ground, it is transported to processing facilities where the raw material begins its transformation. Before titanium can be extracted, the ore must be prepared. The mined material usually contains a mixture of different minerals, sand, and rock fragments. To separate the titanium-bearing minerals from other materials, the ore undergoes several mechanical processes. First, it is crushed into smaller particles using powerful crushers. Then, it is washed and processed through gravity separation, magnetic separation, or flotation techniques. These methods help isolate the heavier titanium minerals from lighter impurities. By the end of this stage, the processing facility has produced a concentrated titanium mineral product that is ready for the next step of refining. However, turning titanium ore into pure metal is not simple. Unlike metals such as iron or aluminum, titanium cannot be easily melted and separated from its compounds using traditional smelting methods. Its strong chemical bond with oxygen makes it extremely difficult to isolate. For this reason, engineers developed a specialized process to extract pure titanium metal. The most widely used method today is known as the Kroll process, named for the Luxembourg-born metallurgist William Justin Kroll, who perfected the technique in the 1940s. The Kroll process begins by converting titanium minerals into a chemical compound called titanium tetrachloride. This compound plays a crucial role in titanium production because it allows impurities to be removed and the titanium to be separated more easily. To create titanium tetrachloride, the concentrated titanium ore is mixed with chlorine gas and a carbon source such as coke. This mixture is then heated to extremely high temperatures, around 1,000 degrees Celsius, inside a special reactor. At these temperatures, a chemical reaction occurs. The chlorine reacts with the titanium in the ore, producing titanium tetrachloride gas. Meanwhile, many of the unwanted elements and impurities remain behind as solid residues. Titanium tetrachloride is a fascinating substance. At room temperature, it becomes a volatile liquid that can be purified using distillation. During the purification stage, the liquid is carefully heated so that impurities with different boiling points can be separated. This process results in a highly pure form of titanium tetrachloride, which is essential for producing high-quality titanium metal. The purification stage is extremely important because even small impurities can weaken the final metal and reduce its performance in demanding applications such as aerospace engineering. Once the titanium tetrachloride has been purified, the next stage involves converting it into metallic titanium. This is done through a chemical reduction reaction using magnesium or sometimes sodium. The purified titanium tetrachloride is placed inside a sealed reactor where it reacts with molten magnesium under controlled conditions. During the reaction, the magnesium removes the chlorine atoms from the titanium compound, leaving behind metallic titanium. The byproduct of this reaction is magnesium chloride. The titanium produced during this step does not look like the shiny metal most people imagine. Instead, it forms a porous, sponge-like structure known as titanium sponge. This material resembles a gray metallic foam and contains small pockets of trapped gases and impurities. Although it is technically pure titanium metal, it is not yet suitable for industrial use. Additional processing is required to transform this sponge into strong, solid metal that can be shaped and manufactured.
To turn titanium sponge into a usable material, it must first be melted and refined. One of the most common methods used for this stage is called vacuum arc remelting, often abbreviated as VAR. In this process, pieces of titanium sponge are compacted together to form a large electrode. This electrode is placed inside a vacuum furnace where an electric arc melts the titanium at extremely high temperatures. The vacuum environment is critical because titanium reacts easily with oxygen and other gases at high temperatures. By melting the metal in a vacuum, engineers prevent contamination and ensure that the titanium remains pure. Another advanced method used for melting titanium is electron beam melting. In this technique, a powerful beam of high-energy electrons is used to heat and melt the titanium in a vacuum chamber. Electron beam melting allows for very precise temperature control and can remove additional impurities from the metal. Both methods produce molten titanium that can be cast into large metal blocks known as ingots. Titanium ingots are the starting point for manufacturing a wide range of products. These ingots can weigh several tons and must undergo extensive mechanical processing before they become finished materials. The ingots are first reheated to high temperatures and then shaped using powerful industrial machines. This process may involve forging, rolling, or extrusion, depending on the desired final product. Forging uses massive presses to compress and shape the heated metal, increasing its strength by aligning its internal grain structure. Rolling passes the metal through large rollers to create sheets or plates of specific thickness. Extrusion pushes the heated titanium through specially designed dies to produce long shapes such as rods, tubes, or structural components. These forming techniques allow engineers to create titanium materials tailored for different industries. One of titanium's greatest strengths is its ability to form alloys with other metals. An alloy is a mixture of two or more elements that creates a material with improved properties. Pure titanium is already strong, lightweight, and corrosion-resistant, but when combined with other elements, it becomes even more powerful. One of the most widely used titanium alloys contains aluminum and vanadium. This alloy, often called Ti6Al4V, is incredibly strong while remaining relatively lightweight. It is widely used in aerospace engineering for aircraft structures, jet engines, and spacecraft components. Titanium alloys are also essential in the medical field. Because titanium is highly resistant to corrosion and does not react with human tissue, it is considered biocompatible. This means the human body can accept titanium implants without rejecting them. Surgeons use titanium to create artificial joints, dental implants, bone plates, and surgical instruments. These medical applications rely on titanium's strength, durability, and ability to integrate with human bone. After the titanium has been formed into basic shapes, it must undergo precise machining and finishing processes. Machining titanium is particularly challenging because the metal is extremely tough and resistant to heat. Cutting tools must be specially designed to handle the high temperatures and stresses involved. Engineers use advanced equipment to drill, cut, and shape titanium parts with incredible accuracy. Depending on their final use, titanium components may also undergo additional treatments. Heat treatments can improve strength and durability, while polishing can create smooth surfaces for medical implants or consumer products. Some titanium parts are coated with protective layers to enhance their performance in harsh environments. Despite its many advantages, producing titanium is energy-intensive and expensive. Mining, chemical processing, and high-temperature melting require large amounts of energy and specialized equipment. However, titanium's long lifespan and excellent recyclability help offset these costs. Many titanium products, especially in aerospace and medical industries, can be recycled and reused, reducing the need for new raw materials. Scientists and engineers are also exploring new ways to produce titanium more efficiently. One promising method is the FFC Cambridge process, a newer technology that uses electrolysis to extract titanium directly from its oxide form. This approach has the potential to reduce energy consumption and simplify production, although it is still being developed for large-scale industrial use. So, why do industries invest so much effort and expense into producing titanium? The answer lies in its extraordinary properties. Titanium is nearly as strong as steel, but significantly lighter. It resists corrosion from seawater, chemicals, and extreme environments. It can withstand very high temperatures, making it ideal for aerospace applications. At the same time, it is biocompatible and safe for use inside the human body. These unique characteristics make titanium indispensable in many modern technologies. Aircraft rely on titanium components to reduce weight while maintaining strength. Spacecraft use titanium because it can survive extreme conditions in space. Medical implants depend on titanium's ability to function safely inside the human body for decades.
Beyond its engineering uses, titanium also has a distinctive appearance. Its natural silvery gray color and ability to develop vibrant surface patterns through oxidation make it popular in jewelry, watches, and high-end consumer products. This combination of beauty and performance has made titanium one of the most admired metals in the world. The journey of titanium, from mineral hidden deep in the earth to advanced materials used in modern technology, is a remarkable example of human innovation. Through mining, chemistry, metallurgy, and precision engineering, we have learned how to transform simple minerals into one of the most advanced materials known to science. Today, titanium continues to shape the future. As industries push the boundaries of technology from next-generation aircraft to advanced medical devices, the demand for this incredible metal continues to grow. Its story reminds us that even the most ordinary elements of the Earth can become extraordinary when human knowledge and creativity unlock their potential. And the next time you see a titanium product, whether it is part of an airplane, a medical implant, or a precision watch, you can appreciate the long and fascinating journey that brought this remarkable metal from deep within the Earth to the cutting-edge technologies of our modern world.